Okay, so let's review the principle of, or the definition of kinetic energy. First of all, it's an energy of motion, which means it's denoted by having a velocity for a particle or a mass. A baseball, a football, a piece of chalk, anything that's moving with some speed will have kinetic energy. And the general expression for that kinetic energy is 1/2 mass times velocity squared. Now, we don't need to worry if we express the mass in kilograms and we express the velocity in meters per second, then the kinetic energy will be in joules. And that's an important point to remember since we will always be calculating in those units. The other thing to note here is that if the speed of the object is doubled, then the kinetic energy is quadrupled. So if the speed goes from 2 meters per second to 4 meters per second, then the kinetic energy will go up by a factor of 4. And that's an important factor to keep in mind in all of this. We'll discuss more about this in a little bit. Now, in this slide, you're asked a very simple question, which is, does a car with momentum also have kinetic energy? And the answer is yes, it does. It must be case. Remember that we know that the momentum is equal to mass times velocity. And now that we know that kinetic energy is 1/2 mass times velocity squared, they both depend on having velocity. So any object with momentum has velocity, and because it has velocity, it is going to have kinetic energy. This slide expresses the relationship between kinetic energy and work. And basically, what it's saying is, or telling us, is that when I do work on an object, I will cause it to accelerate. And if the object is free to move, then applying a given amount of work on that object, and right now we would be talking, for example, a object sitting on a sheet of ice with no friction, or a ball rolling on a pool table, a bowling ball rolling on the floor, anything where the friction is not involved, we can say that applying a force over a given distance will cause it to accelerate by Newton's second law, and therefore acquire kinetic energy. And what this rule tells us, which is also leading into the work energy theorem, which you'll see in a couple of slides, is that whatever work I do on the system will be translated into kinetic energy if there are no other forces acting on it, or if friction is not is not producing heat or other forms of energy. So for frictionless systems, we can say that the force applied to an object times its distance will result in the particle or object acquiring a kinetic energy equal to 1/2 mv squared, and that quantity is also equal to the work or the force times the distance. Now, this slide repeats what we have already just said, which is that the work done on the system will cause a change in its kinetic energy. This is the work energy theorem. So if we apply the amount of work on an object, which causes it to double its speed, then that work will require 4 times as much as the acquiring only half that speed. Or to say it another way, I have an object which has some speed that results in a kinetic energy of, we will say, 4 joules. If I want that same object to have twice as much speed, then I have to apply 4 times the amount of work to that object for that doubling of the speed. And that's just a result of the fact that work is equal to 1/2 mv squared. So if I want to double the speed, then I have to quadruple the work imparted to the object. Now, this slide tells us that the energy theorem also applies to decreasing speed as well as increasing. In this case, we have an automobile headed towards a cliff, and it's imperative that the car stops before reaching the edge. Um, then the work energy theorem says that if the car has some speed uh, corresponding to let's say 1,000 joules of energy, then there must be a braking force times distance, which will bring that velocity back down to zero. So that by equating the two sides, we can say that of the potential the work applied to the kinetic energy lost, then we can say that this uh, automobile with 1,000 joules of kinetic energy must also have 1,000 joules of um, work done opposite to the direction of its motion so that it will slow down. And we can also say then that if it has to slow down in, say, a distance of 10 meters, then I have to apply 100 newtons of force in order for that to occur, because force times distance equals kinetic energy. The initial kinetic energy is, we will say, 1,000 joules. That's equal to the braking force times the distance in which it acts. If I've only got 10 meters for the car to slow down, then the force times 10 meters must be equal to 1,000. So that means that the force must be equal to 100 or 100 newtons. And there will be a resulting change in kinetic energy as by applying this force. This slide asks you to solve a simple problem, although it may not seem simple since you're just learning it for the first time. But consider a case that where you have a fast-moving object similar to the car in the previous example, and I wish to have this fast-moving crate sliding on a floor. We might even say it's on ice floor with no friction to make things rather simple. And we would ask the question of what is the distance over which the or to put it another way, yes, what is the distance that will be required to stop the crate if I apply a given force. So, for example, let's suppose, as before, we have the kinetic energy 1/2 mv squared, which is 1,000 joules. It goes from 1,000 joules down to zero because it's coming to rest. So that 1,000 joules is equal to force times distance. If I were to apply 100 newtons of force, then the way I would solve this would be to use equation D, which basically then allows me to say that 100 newtons times some distance d is equal to the kinetic energy, which I calculate from the velocity, or I am given in joules to begin with. So in this case, we have the crate has 1,000 joules of kinetic energy. We are going to apply a retarding force of 100 newtons. So the distance that's going to be required is given by equation D, which says that 100 newtons times D is equal to 1,000, because 1,000 is the change in the kinetic energy as the crate goes from some velocity v down to zero. And so I can solve for the distance D. Now, this question asks us to consider two cases, one in which the car has some initial speed, which we will say is 10 meters per second, and the other one is the same car or a similar car of the same mass having 20 meters per second as its initial velocity. And if in the two scenarios the frictional force is the same, uh, how much extra stopping distance is going to be required for the same car going twice the velocity of the original car? What is the what would be the stopping distance if we double the speed? So it could either, the options are that's actually less, which we've clearly excluded as we've just as I've been rephrasing the question, which is that we know that if the initial speed before braking is doubled, that the stopping distance for the same frictional force certainly cannot be less. It has to be more. Is it about the same? Is it twice as much? To figure this, we have to apply the equation force times distance equals 1/2 mv squared. And if I double the velocity, then I double the amount of work. I'm sorry, I quadruple the amount of work because the work done is 1/2 mv squared. V has been doubled, so the work required to slow it to zero speed has in fact quadrupled. Now, conservation of energy is probably the most important physics principle in all of physics. It basically allows us to calculate various properties of moving objects, whether it's its speed or its momentum or how long it's going to take to come to rest. It's used universally in many different applications. But simply stated, the law of conservation of energy says that if I calculate the sum of the kinetic energy and the potential energy of a system, it could be two particles that are hitting or colliding towards each other, for example, or it could be one particle that is been thrown up in the air and will start to will slow down until it changes direction and comes back down. But however I regard it, the sum of the potential energy plus the kinetic energy, in the absence of friction, will be conserved. That is to say that either before or after a collision, the total energy is the same. Now, there are cases where there may be heat created when two objects collide with each other, or there's deformation of the crumpling of the automobiles when two um, objects collide, in which case there may be heat generated as a result. So in the final state, after the collision, we have to add up not only the kinetic energy, but how much energy went into heat. And that must be equal to the energy before the collision occurs. And that states a conservation of energy principle, that the sum of all the energies of the system of particles or objects must be the same before now as later, or before in a collision as after a collision. Here we see a very simple example of the law of conservation of energy applied to raising an object and then dropping it from a high elevation. And the conservation of energy principle here states that the energy of the object is going from potential energy, which we create by pulling on the pulley to raise the object, to allowing the weight to drop freely under gravity, and in doing so, it acquires kinetic energy. The conservation of energy says that the potential energy before we release the rope is in fact all the energy available. There is no kinetic energy. The object is at rest. When we cut the rope, the object begins to fall and it increases kinetic energy. When it arrives back to the ground from the same elevation at which it started, then at that point its kinetic energy is equal to what its potential energy was before we cut the rope. And so the total energy is conserved. In the first case, the total energy is all potential energy before we cut the rope. After we cut the rope, the total energy is all kinetic energy when it returns to the ground. Now, the bow and arrow also gives us a scenario where conservation of energy can be applied to explain the motion of the arrow after we release the bow. So initially, we pull when the bow is pulled, or the string of the bow is pulled back with the arrow loaded attached to it. We are increasing the potential energy of the system. We have applied a force against the restoring force of the bow. That force was applied over a certain distance. That product of force times distance is the potential energy that we have created in the bow. When the bow string is released, then most of the potential energy is transferred to the arrow as kinetic energy. But some of it goes into the heat or heating up the bow. And heat is another form of energy, as we will learn in a few later chapters. So the conservation of energy says that I create potential energy by pulling on the string. When I release it, some of the energy goes into 1/2 mv squared of the arrow, where m is the mass. Where m is the mass of the arrow, and a small amount of it goes into heat. So in the next question, you'll be asked to look at this, and we'll resume after you've had a chance to review and answer the question.